Right, guys. Okay, the microphone seems fine. If anyone complains, just tell now. One note, the things that are smaller nowadays are generally faster. Optimizing for size is optimization for speed for most algorithm that you can do. Not always, but almost always. So if you optimize for size, you optimize it for speed. So this is just out of the way. This is the standard in practice. And I'm doing this talk is because I was really impressed by that thing. And you'll see soon why. I'm really happy to be here and to present it. So there we go. The next part is the slides. If you ever want to have the slides on your phone or anything, you can take a picture and have them later. And the other part is that I want to know if any of you, or how many of you use command line tools like at least once a week. I suppose most of you. Lots of people. Cool, very cool. I suppose some of you might already know what this standard is because you heard it. So with that, just move next. So we start here. If you remember the first talk, it was around Windows 3.1. This is 95, even though this part existed. I was programming at that time, and RAM was very scarce. In a way, it's really scarce, and you wanted to get something, but it's quite expensive as well, and the processors didn't support so much RAM. So you get with some cool tricks to be able to increase your RAM. The sheer truth, and what this talk is not about, is getting more RAM, or getting more of the things that you need to get them. This doesn't work, it's just broken. This particular case, SoftRAM 95 was for Windows 95, and it came around that time. And like I said, there was not enough memory, and people wanted to have more memory. Stuff was constantly loading from a very slow hard drives, spinning and all that. And it was real scam. It uses memcopy instead of compressing memory, so it effectively actually ate memory. And the joke was, if you want to have 4 megabytes of memory, you can just install this thing instead of having 16. So this talk is, to put it simply, not about memory compression. It's about disk and network. And now the previous part was about downloading memory, which is a meme and all that, but downloading this is real. That's the cool part. If you look at half the graph, just in the middle, this is Playtech. It's a production site, even it's a demo site. This one's a particular demo site. It's not a real money site, but it's very much real, treated as real goes. So, and if you see the middle of it, the first part is how much we write in kind of raw kind of data. It's lines, but you can consider it raw data. And after the mark is what happened after this standard was enabled. It pretty much halved the amount of we write to the disk, even though we have the same input, we route half of it. And I want to stress, the before part uses gzip or deflate, and the other one uses this standard. It's not just compressing it, but doing it way better. And if you notice, the CPU utilization, which is the last graph, more or less remained the same. There's a slight uptick there because there was more activity on the site. This site is infested with bots, where people put them on purpose there. So that's how downloading memory works. And this is pretty much what you need to know. It actually works. So before going into compression, and why I wanted to do the slide, this particular one, and the entire talk, is the few pioneers in compression, which gave us really a lot of things we don't remember. No. First one is Huffman. And Huffman encoding is very, very popular. It's pretty much everywhere. Almost any compression algorithm, any format, JPEG if you think, even it has the compression part. Standard zip files have the compression fact of Huffman encoding, which is not really compression. It just finds the things that are mostly used and assigns lower bits to them. And the other two guys, which in 77, which Abraham Lempo and Jakub Ziv, those are two important guides, and this is the prime reason I wanted to do the talk, besides how amazing this standard is. They passed this year, and in the spring, both of them, which is kind of very interesting part, that the pioneers that started IT or computer science, they're just getting away. So they created LZ77, which is 77 is the year that was created. It's older than me even. And it's pretty much the backbone of most compression algorithms, or everything that it makes data small nowadays is somewhere there with different flavors. And the other one that I want to mention is LZW, and this is Terry Welch, added some work to the previous two guys, like Abraham Lempo and Jakub Zev. And he created the so-called meme, GIF thing. Well, back then it was not meme, it was very contested format. But one of the things that happened then is that this is one of the most elegant, if I look for a word, elegant algorithms that I've seen. It's easy to implement, and if you're ever interested in data compression or anything that it relates to making things smaller, understand how the bits and bytes work internally, it's a good algorithm to implement. I implemented it in my teams in assembly because, I used to use assembly, so it was cool. And it was, better than other implementations, so I had to make it in something. But anyways, this is the algorithm that created GIF, and later down was moved to Unisys. Unisys held patent for 20 years, which make GIF pretty much impossible to create unless you pay to Unisys. So, anyways, the next important guy is Philip Katz, who is dead, also very young age, younger than me even. And he created Zip and Deflate and gave them to the world. This is one of the nicer things. Made it open source effectively, there's RFC for it. And the rest after that, the story after Zip, it's pretty much everywhere. It's a synonym for just compression and putting things together. And the next part is you have better compression algorithms, but better is kind of, how to say, harder to tell if it's better. They're slower, they're denser, and the important part comes with Jan Collett, who created this standard, which is the entire talk about, and you see how cool it is. So what is this standard? It's this thing that you see on the screen. And this is a real picture. This is Microsoft Store. When you try to get this standard, you get Bible. That's how it works. How it happened, I wanted to get this standard to be installed on our Linux boxes in production and everywhere. And this surprisingly was amazing,ly easy process. I can't believe how easy it is. I have to mention it on the talk. It was easy. And props for the guys, they know. Thank you guys for doing it. But this part is getting it on Windows boxes that are, most of the developer boxes are Windows boxes. And getting it there was actually very problematic. There's a lot of security part that you have to pass, and they don't want you to do it. It's dangerous and all that. So you get Bible instead. And this is what you work for this standard in Microsoft. It's not popular, even though it's amazing, like godlike, amazing. I know I'm just talking about it. It probably will be justified soon. But the reason I think it's amazing, because personally, I'm really rarely impressed by technology, especially IT. If it's mechanical engineering, something like that, that's cool. This I don't know how it works. But most of the computers and stuff, I would generally have a decent idea what it does, how it's doing it, and what you can get, what the ballpark numbers. But this part just took me really by surprise. I remember the first time I ran it, I actually think it didn't do anything. I had to copy the file to another place just to see if it does anything. So it was a really great thing to do. And what really is, however, it's just boring. Maybe not boring, but kind of boring closeless compression based on TLZ77. Everything's based on this thing called model. It's created by Facebook, which is kind of interesting thing for me to come on the stage and present Facebook, which people that know me will share my kind of lack of appreciation or disdain or that kind of thing. And I want to say it's still amazing engineers, really talented people work there, and they produce things that are given to the public. The algorithm is, if you okay, any of you watched Silicon Valley? All right, that over there on the score, Weissman score, is the thing about the algorithm. This almost fits the narrative of the TV show. It's almost like, art imitates life, that kind of a thing. It is that how amazing it is. They had the score that which is comparison with a standard algorithm and how dense and how fast it is. This kind of does the business. But what's really amazing about the algorithm is not even the compression, it's the decompression, which means something small to make it big again. This is pretty much unmatched. I have not seen anything that even comes close. Density, you can find other things that are orders of magnitude slower, but they do stuff. And the interesting part, at least through mirrors, when I found that, it was, I was very late on the party. Well, it happened this year, but several months back, to be fair. And when I found out that it's actually used almost everywhere, and many people already know, and I'm a kind of this little guy, goes to a party, everybody's half drunk, or having fun on the floor, and I'm just there, what's happening? Why nobody invited me? I used to do those things when I was young, and I don't know nothing, anything. So this is a quote from Fedora implementation for better FS, and it pretty much tells you what you need to know. I mean, don't read it. The font is done on purpose, so you can't read it really is on the screen, but it is something that is part of the Linux kernel. And if there's any project or any kind of piece of software ever created in the last many years that has given more to humanity, it has to be the Linux kernel. It's amazing collaboration, to put amazing one more time. It's beyond amazing. It's probably one of the better things that we have as a humanity when it comes to software. And it's there inside. You get there extremely hard. Things don't get there. Back in the days, some folks from Java wanted to put ability to manage the memory controller from the user land, and this didn't go there. It would have allowed Java to have better garbage collector, because instead of copying blocks, you can trick the memory controller to rearrange them and keep them flat for you, if you know how generation-based garbage collector work. They copy things around, but instead of copying them, this memory bandwidth and all that, and latency too, you can just tell the memory controller to arrange them for you. And the interesting part is used not only in the kernel, but it's pretty much everywhere. Arch Linux even uses this standard feature for its own distribution. Intel recently, like just a month ago or a little bit more, announced that they're going to support in the hardware. Literally, they added hardware features to support the matching of the algorithm. It's that amazing. So I suppose most of fans are here not League of Legends, but Dota. So anyways, League of Legends had a great article several years back of their patching mechanism. They use this standard for effectively compression and decompression, and it's a really great write-up. If you have the slides, there are links in the speaker notes, so if you want to find it. Many databases use it, both for networking, for compression on the disk. Compression on the disk, I say things that are smaller. If you have great compression ratio, you can get faster reading from the disk, and also IO's throughput reduces greatly because you write significantly less. So if you get that, it's just nice. Blender uses it as an internal format from not very far, a long time ago. So pretty much everybody got there, and I'm the last one. So the sheer truth is that this is really well created and very well engineered algorithm. I would say algorithm, it's a set of tools, but the core part of it's like in the Silicon Valley is the algorithm. Everything you build around this little gem inside. You build it around. Of course, you want to build the rest of engineering to be great and to be enjoyed by people and to actually be able to serve real purpose. But even the code, normally if you see C code, you scared and stuff and things. I never, for the amount of languages that I know, I have actually never known C. Like I never started a project in C and finish it. Unless you count microcontrollers, but you don't count them. That's kind of, it's easy. So, but even this code is easy to read, easy to follow. It's well written, it's well documented, it's well engineered. Even the first 4 magic bytes. Anyone of you that have not heard it from me knows what magic bytes are. Okay. Most formats, compression, image, have usually first few bytes tell you what they are. GIF files start with G, I, F, 87 or 89. Nowadays, all of them are 89, A. And that's how they start. Zip files start PK, the guy that I mentioned before, and zip. gzip starts with its own magic byte of 10 bytes header and so on. And this one, it has its own. And they engineer it in a way that the letters, if you take, let's say, GIF, you can find it in any text document. But this part is a sequence that it cannot be even Unicode. It's even reserved for Unicode. So you put things to make them as easier to use and as fault-proof as you can get. The code is available at GitHub and all that, So the important part, however, is how we can make use of it, because the talk is about practice, not about how amazing it is and godlike and all that. It comes with a set of tools that are very similar to existing tooling like gzip, zip, xz. Very similar syntax. The switches, the optional parameters, and so on follow the same principle. The only difference maybe is that it keeps the files. If you use gzip to compress a file, it just deletes stuff to it. It's really annoying. I can't get used to it. So you have to keep putting K. And the other better part is a drop-in replacement for existing formats. At the library, if it recognizes these magic bytes, okay, that's not me, this is gzip or this is xz. I'll just do that one. And that's how it works. You can install it quite easily if the standard distribution doesn't have it. On Mac, find out that you can install it with Brew, which put the library in a really funny place, but that's a kind of a different story. But the best part is that you have how you get it on Windows. Actually, getting it on Windows is the hardest thing ever. Most people use 7-zip or something like that. The guy, Igor Pavlov, does not want to support it. Well, I don't know, just doesn't want to build it with ZSTD as a plugin, because 7-zip is actually a set of plugins that are invoked when you find stuff. And it doesn't want to do it. There are alternative versions, but those versions kind of not approved. They're not so kosher and all that. So we find something called nanozip, for example, and pzip supports, for whatever reason, it has some kind of a little bit childish interface, so people don't like it. It's kind of this green leafy TP and so on. So we have some time, and I will try to do something that is not very easy now. I have to switch the screen to be shared with me, and I want to show you how it actually works and what it does. I'll try with duplicate, and I hope you'll be able to do something, please. Okay. I have the same, and I have the same. Okay. So this is Windows subsystem for Linux, and there you go. That's 4.4 some Linux version. It has ZSTD. And this is the installed version. This is the latest version that you can get. Just, I don't know how well it's visible, it's not visible. Guys, do you see it at all? All right, cool. Maybe I can try to increase the font, I don't know. Anyways, pointers. I have some files here. Some of them are actually things that we do. For example, the file a server log and la is a Playtech log file, which is 50 megabytes of just text. Maybe this is easier. Well, this is slightly better. So I'll just demonstrate compression with gzip, which is very standard and everybody knows it. It's just what the deflate is, which is the standard thing what you have with any zip. Anything you receive a zip thing is the same as gzip. They're very similar. The only difference is the directory structure. So, example for compressing with gzip is something like that. All right, and now I'll do the same thing with ZSTD. This will be the default compression layer, which I don't even use. What we use for further, I use 10, which is generally high compression layer. It will be very similar, but the differences will be quite drastic as well. This will take time. As you see, the compression times are very, very similar. You know, like pretty much the same for practical purposes. And this is the result. It's twice smaller. This is standard texting that we do. It's just is twice more, that's it. It takes same time and produces twice less content. The compression is even better. I'll show that part as well. That was not what I wanted. All right. All right. We deleted it successfully. Like I said, I hate how it deletes it. Yeah, that's the part. I have to do the same thing part somewhere here. Please don't. No, okay, I can delete it this time. Dear goodness. All right. Nothing's working now because we kind of went sideways. Fortunately, this one is still here, and we do it in reverse. Okay, it's 65 milliseconds it takes to decompress it. So, since we have it now, we can compress it back and decompress it with the other guy. Okay, please. All right, similar results. Oh, come on. All right, fine, almost there. As you see, even the results are around more than 3 times slower to decompress. And this is simple text file. One of the worst things about deflate LZM 8.2 is that they are absolutely suck on already compressed files. I have one RPM here, which is installation of some of our servers. It's RPM, we use RPMs for them. And I can do the same thing with them. This is this one. Just for the sake, I can use the same compression layer, which then, if I use lower one, which is the default is 3, and it's around 3 times faster than the other one, it's even better. But anyways, we put even higher compression level because if you distribute binaries, you probably want to compress them as much as you can because you do it once. So I'll put something generally high. The compression levels vary. 19 is the maximum. There's experimental with 22. You can use them, but you need more flags to do it. So this is pretty much standard compression of a file and how much it takes. All right, it took around 3 seconds. And as you see here, it's slightly improved, but it's still compressed. It's already compressed file. It doesn't really get better, even if you try harder. And now the same thing, we can do it with gzip. And it takes it more time. That's one of the issues here. Okay, it took the same thing. Fine. Which is okay. Generally, for compressed files, the difference is this is quite high compression, and what we want to do now, they're pretty much same sizes, so you can't really compress them. The other option, usually the files, most of the distributions are actually compressed with ZSTD. They're compressed with something like XZ, and XZ will be really, really bad if I try to do it. Probably will take a minute or something. At least the decompression is super fast. And if I try something quite different, like this one, this will take probably a minute. I hope it will take a minute and not more. I'll try to kill it in a minute if it doesn't work like that. So this is XZ has much denser compression than gzip, and generally it's used by quite a few distributions to compress the files like that. It's really bad at compressing already compressed files. For whatever reason, Deflate was not so bad at its own standard part. But the good part about this standard is that it's really, really fast on the compression. So even if you take more time or use higher compression parameters to compress it as dense as possible, the outcome during the compression is even better if it's more. Like I said, if you optimize for size, you usually optimize for speed. In this particular case, the searches and the hash tables are denser, and they take less memory. So you need to less because the output will be the same anyways. So but your input is denser. So actually, the decompression is slightly better. This is still going somewhere. I don't know. There you go. We got it. 55 seconds. This is if you use tools like XZ with the default compression. And just examples for I have other files here as well, but that's kind of the point. If you consider it as drop-in replacement to gzip, it's just denser for similar compression levels. For similar compression times, it's denser. And if you consider it as a default, it's just much faster. For example, if I compress this, some of the other files here, let's say we have this demo, which is some log files as well. This will be the default way to do it. This will be very, very fast. Try the similar thing with it's over 4 times faster. And just to prove that it's denser and it's smaller, what you actually care, it is, and not trivially at that. This is one of the things that totally took me. I couldn't believe it. Like I said, I copied it. It was so much faster. They don't expect this thing. And the prime reason for this was that before you get there to this today, you had the premise that you generally can trade speed for density, but the trade-offs are not good. So pretty much the default and the fastest one are the ones that you want to use. So I can probably get it here. Okay. Right. Up. So that's examples of Playtech files, and this is what we generally had. Playtech, for better or worse, uses massive text files. It's very simple, and you always have easy tools to actually manage those files. You can use the dumbest tools that you have, the dumbest text editor or grep or less or anything that you can find, and they work. There are certain ways we write the files, we put all the information, and they're very highly compressed, as you witnessed. The compression is around 20 times. We have tooling. Most people love generally the files. It's one of those things that people at Playtech learned the first, at least in my department, learned to use them. However, even with compression, with Deflate, actually, really a lot of them, like really a lot. We pretty much can afford to keep them for 1 month. That's it. And we probably, in some newer sites, can maybe have a little bit more space, but consideration is a non-trivial argument for them. And this is what happened with one day, files. Nova is the name of the server, which is the main application server for us. And this is 1 day of files. You can see them. On the left side is ZSTD, on the right side is standard one that we have gzip. This is production, 1 day on some kind of not a big site. It's around 2 gigabytes for one server. And the difference in search, which use grep for search, is just drastic. It's twice faster. It improves not only the storage, which is kind of a concern, but you improves your daily routine. And that's not a trivial amount of improvement that you have. This is a similar example with something called gateway, which all the traffic goes to gateway, but it generally creates less logs. And it has, as you see, it's around 4 times smaller, and the things are pretty much maintain 1-to-2 ratio. This part is something that kind of, I can tell that this is what makes it so much worthwhile and was so interesting to have. There's another part that I want to go, besides the tooling that you can use for log files. You can use it for binary ones. And one of the things most compression algorithms allow you to do is to set a dictionary. This is a great set of data that it can be bought on compressor and a decompressor side. If you have client and server, they have to have them. Web nowadays have the compression algorithm called Botley, which comes with, in its own RFC, comes with tons of hex for the dictionary. But what ZSTD can do, it can do even better. You can get existing binary distribution or file or set of files, if you make them with tar, and use it as a dictionary to a new deployment. So your own new version, you can use the previous version as a base, because you know that you already have it there, it's there. So, and you can make very nice and small and very fast to decompress patches or new roles or versions, whatever you call them. This is one of the extremely cool features that is just part of the standard set. It's just there. You get it and it comes. You don't have to do anything more. However, this talk will go nowhere unless I do the important part, at least to me, is using this standard library, which comes from Facebook and you can get it and so on, in your application, not as a standalone tooling. Using a standalone tooling, you really can't do it network traffic. I mean, it's not impossible, but it will be almost impossible, and it's very cumbersome. And if you want to do some of your own formats, and they have different types of data, something is compressible, sometimes you have headers and whatnot, you will not use ZSTD anyways. Like I mentioned before, Blender uses it. So using the library is probably fundamental if you want to deploy your applications. And one of the super nice things about the library, when I found out, is that API is so easy to use. And actually, for compression thing, it takes literally one function. It has void pointer with the input. It has a reference to the compression structures, and a void pointer with size and a pointer to the output. And that's it. And it has one more parameter if you want to flash the data or you want to enter compression. You use that one till you have input, or you run out of output, so you have to flash the output, sync it down, and that's all it does. As a kind of proof of the entire part, I implemented using it Java with GNA, and then it works. The guys from Playtech even use it today. With the particular implementation, it's linked there in GitHub if someone wants to check it out. It has implementation for input and output streams. It works very similar to gzip. Well, you have to put ratio, because I thought that people should know about it and not to assume the default one. And the next important part, if you ever do that, and I suppose most of you do not use C directly or Rust, you need to care if you have managed languages, this Java, Go, that kind of a thing. In this case, you want as big buffers as you can get. You don't want the overhead of going from your managed language like Java or Go to native code to dominate the speed, the performance, the cache trashing. So you want as big buffers as you can humanly afford, both the input and output, and that would kind of set you free. The last part, that is kind of the last in certain ways, is that if you choose to do it, you have that part that is in C, and it's a native code. And very few people actually easily get native code and put it in the application, especially if it's some cassette like Java. You won't do it, it's right to answer everywhere, but then you need to compile the libraries for Windows, for Linux, for Mac on ARM, like M1, M2, so you get a lot of that part, and this is the minimum the deployment that will be in the company. And if you use some ARM servers, you need ARM servers too. So you will have to compile the library cross-compiled, which is kind of annoying, and if you don't do C, cross-compiling is annoying. So you might be really tempted to do one other thing, port it. And that slide is there because actually I did try to port it, and even succeed. And I tell you not to do it. It doesn't worth the effort. It's really hard. Any mistakes will be punishable. I managed to port the C part compression, only the compression part because I didn't care about the compression in Java. It didn't work the way I wanted. Internally, this standard has multiple algorithms for matching, and I ported only one of them. And the harder ones are much harder. You probably wouldn't have used them, but I ported one of the easiest ones, which I didn't demonstrate now. So we're actually using something else. So my advice is get the C library and bite the bullet. Get it in the code. Use it in the code. That's kind of something that's not easy to do if you have not done it, but you have this conference and the guy sitting in front of you tell you, just do it. Don't try the other alternatives. And the other part is that the library is actually really well written, well maintained, the bugs are fixed. And if you port it, you probably fought through the bugs. Recently, the very last one was fixed a bug, but some people in Google with a lot of work managed to find some specific case that it managed to create a corrupted compression. And we managed to I'm kind of almost on time, so give or take, to end up to the end of the part. How the entire talk happened and why I really wanted to do it, besides the two guys, Lempo and Ziv, that died this year, is that I was trying to fix our own logging. We had problems with it. It's asynchronous fully, but there are cases when you lost logs because, well, we produced too much or some other variants of this. And I rewrote the entire logging, which is written for some version of log4j, but it's pretty much entirely Playtech code by now. So we rewrote this entire part, call it parsley, which uses a fat 50 megabytes of direct byte buffers. It doesn't do any lazy evaluations and all that. It was quite and was put a lot of metrics as well. And one of the notices is the deflate part, which is only the deflate part, nothing else. Took in some cases up to 6 seconds per minute. 6 seconds. This is 10% of your time you're just doing deflate. That's just ridiculous. So then I looked for algorithms. I knew, like I mentioned, I knew deflate, LZML, LZ4. Those are the algorithms that you get faster, but they're not denser. It kind of sucks. It feels it's not an improvement. Why would we do it? I mean, okay, it's just work, maybe a little bit, especially for online work or online processing. It just doesn't work. Then I found this standard. Like I said, now it's kind of history. It's implemented into production, but putting it in production was not easy. Took an effort, convincing. I have my own cloud to rely on to convince people to do things. But I said, if you can at least point to this talk and tell the guys did it. They did it. It's great. So I managed to put it, and now it's down. I have very little time left. I think I'll be able to show, and this is production data on a quite big site. Just have to somehow manage to drag it to the other screen. This is, I don't know if I will manage to succeed. Okay, not bad. So now the interesting part is that I don't know what it is showing, and I don't know, this is 7 days, all right, okay, we're having something. Right lines, and we don't have anything useful on the screen. What? Okay, so I have to scroll slightly up and it will be nice. Okay, just. This is live production access data, and yes, the scroller is missing. No, it's still here. I just don't see it. All right, this is what we're looking. At least I think. Okay, yes. You can see it when it was enabled. I suppose it's kind of visible around that part, around 9 days ago on Tuesday. It was enabled, and you can see the data is significantly lower than on the left side of the graph. Right lines are very similar. They vary with the days, the daily activity of people logging in, doing whatever they're doing, playing, logging stuff, and the CPU utilization is more or less the same. So that was my goal. CPU the same, less writes, faster reads. Like I said, that's very live. I can put the last minutes or anything, but it is. So that is my story with this standard. I managed to kind of get in production and live, and I'm personally almost humble to say impressed with what people have managed to have done. So I think that's it. I thought that I would have 5 minutes. I know I probably spoke too fast, and most of you didn't understand anything. But if you have questions, I'll be very happy to answer anything.
That is a nice story. Thank you so much for this. This truly feels like a real-life Pied Piper, if anybody's familiar with that.
Almost, indeed.
I wonder what's the support from the browser side on this?
Okay, browsers technically exist, but browsers are not there. They have Botley, I mentioned it. And what Botley does, it has a dictionary. And dictionary will probably always be better because it's the most common HTML, CSS, JavaScript, everything's in the dictionary. So you don't need to vary the same small files because in the browser you have always small files. So what if this will be dominated by the fact that you can bootstrap the compression and build a dictionary instead of having the dictionary already there. So Botley is there. If this standard, for whatever reasons, gets similar dictionary, it will be really good. It will be better than Botley because it is better, but currently it's not planned, or generally those things take time to get there. One thing that I probably say, it's not browser, but if you have anything like games you develop or something, use this thing for your packaging. You don't use Deflate. Don't be like Larian and like Baldur's Gate and other things. Don't do that.
This 3 and 4 times compression starts me thinking that what's the mathematical maximum of compression we could get out of anything?
Okay, this is actually a very hard one because the closer you get to the absolute maximum, it gets exponentially more time to find it. First, you have to find the longest possible sequences that will be matched. So, and this I think it's probably all N3. I'm not actually certain it's on 3 or it's ON 2N at some point. Then you have to find. Then you have to represent them with the lowest possible bit. So the longest ones have to get the lowest possible bit. So you have to pretty much do it multiple times to see which one is it. So this doesn't work in practice, and that's what I mentioned.
Yeah.
That if you try to do it, the time to do it is too much. It works using the very high levels for if you do distributions, like binary distributions, this works. But it doesn't work to do it anything online. It's just not that. The differences in between them is like a fraction of a percent, like 0.23%.
Yeah, pretty cool.
Yeah.
Questions from the audience? Just raise a hand. There is one in the front. Let's pick that first.
Are there any good reasons not to just use compression level 19 for almost everything?
It's awfully slow. To do it, I can demonstrate it. I didn't want to demonstrate because there was just not time. If you distribute, let's say, if let's say do your Arch Linux and you want to distribute, you absolutely do it. You want to do it. If you want to distribute, and it's one time. But our case, we are writing log files on the fly. You're doing networks on the fly. For example, Kafka does that. It's not very good for Kafka, but doesn't matter. Kafka has ZSTD as a compression option. If you do it on the fly, you almost get nothing out of it. Like I said, you get fractions of midgets of a percent for orders of magnitude more efforts, CPU time, energy, everything. Yes, you generally want to get a trade-off that suits you. You can't just... The general tree is pretty good for most people. I put 10 because I wanted to match the CPU, also looks good on the graphs.
Thank you.
There was another question there. Yes.
Hey, so in the decompression phase, you showed the times that the decompression took, but I noticed that in the kernel space, it took actually 2 times less with the C standard than with the gzip.
Yes.
I would assume that they both do the same syscalls, so why is there this time difference?
All right, it wasn't visible. The data that you have to get to carry from the kernel, it's twice less. You get twice less data to carry. That's kind of the sizes are written below. You mean on the slides with the one-day examples? That one? Oh, you meant the demo? Yeah. The reason is that this standard is more dense, so you have less data to vary from the disk or whatever sans or whatever you have significantly less. So that's it.
Okay, actually, it makes sense now.
Yeah. Okay. Cool. I didn't explain it. It was because I put the size. Kind of it's obvious. But okay. Fair point.
One more question?
All right then.
I'm not going to let you go unless there is one more question.
All right, guys, from Playtech, you have so many, probably wanted to ask anything that you cannot credit at least 6 times.
Okay, let's give a big round of applause for Stanimir.
Thank you, guys.
Thank you.